Welcome everyone to this explainer. Let's jump right in. I was recently digging through some totally fascinating source material on a massive breakthrough in the Java ecosystem called BlindBean. Today, we're exploring exactly how it makes data privacy mathematically ironclad, yet honestly incredibly accessible for Java developers. We're talking about homomorphic encryption, a concept that usually requires a PhD to implement safely. Well, it's now been simplified into something you can literally use right away. I absolutely love this guiding vision because it perfectly captures what BlindBean is all about. The whole goal here is to make complex cryptography completely invisible to you, the end user. You shouldn't have to rewire your entire engineering brain to secure your data in use. Instead, you just interact with your domain objects like you always have, and the library handles all that heavy cryptographic lifting totally behind the scenes. So, here is our roadmap for today. Number 1, we'll meet BlindBean. 2, coding with BlindBean. 3, its 3-layer architecture. And 4, the guardrails and limitations. Let's get going.
Okay, Section 1, Meet BlindBean, the invisible cryptography.
To kick things off, let's get a quick handle on what we're actually dealing with when we talk about homomorphic encryption and why it's such a massive leap forward. The crucial takeaway here is that it allows you to perform secure, private arithmetic on encrypted data, and the result perfectly matches what you'd get if you did the exact same math on raw plain text. Imagine being able to add or multiply user balances right inside your database, while the server itself has zero ability to read the actual numbers. It's like doing a puzzle in the dark, but the pieces magically fit together perfectly. To really put that into perspective, look at this comparison. In standard apps, you've got this massive vulnerability window. You have to pull encrypted data into memory, decrypt it, do your addition, and re-encrypt it. You're exposing raw data right in your server's RAM. But with BlindBean, that window is completely gone. You just calculate directly on the ciphertext itself.
All right, moving on to Section 2, Coding with BlindBean, the developer experience.
So how does this actually work for you day to day? Well, the workflow is incredibly simple, and as they promised, it acts just like hibernates. Step 1, you just slap a blind entity annotation on your domain class and a homomorphic annotation on the fields you want to secure. Step 2, you compile, and BlindBean generates a highly optimized proxy wrapper. Step 3, you just call straightforward methods like add balance on your wrapper. That proxy seamlessly handles all the complex ciphertext extraction, the homomorphic math, and the reassignment for you. What's really fascinating here is how they avoid runtime performance hits. Instead of relying on slow reflection APIs, the library generates source code directly at compile time, using abstract syntax trees. Plus, it actively prevents you from doing something, well, kind of crazy, like trying to mathematically multiply text strings. It simply refuses to generate addition or multiplication methods for string or Boolean fields, so it acts as this great automatic guardrail for your domain model.
Let's dive into Section 3, the 3-layer architecture under the hood.
Now that we've seen the magic trick at the developer level, let's look at the deep architecture that makes it lightning fast. BlindBean is bleeding edge. It requires Java 26 and heavily leverages Project Panama's foreign function and memory API. This is absolutely critical because it allows BlindBean to achieve zero overhead native calls to underlying C++ cryptographic libraries without relying on those traditional, clunky, and often painful Java native interface wrappers. Digging deeper, you've got 3 core mathematical schemes to choose from, depending on your use case. Palier runs in pure Java and utilizes the vector API for arbitrary integers. But if you need fully homomorphic encryption, you look to BFV for exact 64-bit integer arithmetic or CKS for approximate floating point real numbers. Both BFV and CKS bridge out to a highly optimized native C++ engine. And that native layer connects directly to Microsoft Seal 4.1, which is a total industry standard for fully homomorphic encryption. Because the library is managing native C++ heap memory right from Java, BlindBean enforces strict auto-closable patterns. This guarantees that absolutely no native heap memory leaks occur. Plus, the whole thing ships as a single static DLL, meaning you don't have to install a mess of external dependencies on your host machines, a huge win for deployments. If you need speed and massive scale, you are going to love this. The native BFV scheme allows for single instruction multiple data, or SIMD batching. By just passing a simple long array in Java, BlindBean flawlessly maps these massive vectors across the FFM boundaries, right into the underlying polynomial parameters. You can process literally thousands of variables simultaneously at the C++ layer without adding a single millisecond of overhead to the Java invocation.
And for your CI pipelines, we can't forget about testing. The test support layer provides a simple BlindBean test annotation that completely removes setup boilerplate. It automatically manages the complex native lifecycle and context initialization behind the scenes. This ensures that absolutely no cryptographic keys or native handle memory leaks happen between your test methods.
All right, final section. Section 4, Guardrails and Limitations, Hard Engineering Boundaries. Cryptography requires strict rules, and homomorphic encryption has some very unique constraints. First, understand what this cannot do. You cannot do conditional branching on encrypted data. There is no less than or equals check without decrypting first. Second, homomorphic math requires data malleability to actually work. That means the ciphertext doesn't protect its own integrity. You must rely on standard database controls, like record-level max and permissions, to ensure nobody maliciously alters the stored encrypted values. Now, here's a massive gotcha. As you perform math operations on BFE or CKKS ciphertexts, especially multiplication, you spend what is called a noise budget. Every native ciphertext carries this finite budget, which begs a very, very important question for your application stability. What happens when that noise budget hits zero? Well, the answer is critical, and honestly, a bit scary. If you don't monitor your budget and it hits zero, your application doesn't throw a neat Java exception. Nope. Instead, your data silently decrypts as corrupted garbage. This is exactly why monitoring the provided noise budget metrics in your observability dashboards is absolutely mandatory for deep computational chains. You also have to pick your scheme carefully based on your domain. Never, ever use the CKKS scheme for financial data. CKKS is approximate by design. It essentially trades precision to manage its noise budget. If you are calculating money in cents and you need exact round-tripping, you must use BFE or Pallier for sure. And commit this number to memory, 8192. This is the absolute minimum polymodulus degree limit you can configure in BlindBean. Sure, lowering it might theoretically give you a speed boost, but it would silently downgrade your security. 8192 is the absolute floor required to maintain the homomorphic encryption standard for 128-bit security. Finally, let's talk key management. When it's time to rotate your keys to comply with your security policies, you can't just do it in place. Because the ciphertexts are mathematically bound to the exact keys that produce them, you're going to need to write a batch job to decrypt the records under the old key bundle and then re-encrypt them under a fresh one. So, with the complex math hidden seamlessly behind simple Java annotations and the native performance heavily optimized through Project Panama, BlindBean really does remove the traditional friction of homomorphic encryption. We leave you with this to consider: how will you use this invisible cryptography to build mathematically guaranteed privacy into your own architecture today? Thank you so much for joining this explainer, and hey, happy coding!